when we continue talking about machines today, our learning objectives, same learning objectives as last time here. So I'm not going to go through those. A couple reminders on the homework. This is due on Tuesday night. Remember, this is that specific term or that specific text telling us the pin C exerts on member ABC. This is different than like find the reactions at E. And so we have to do that one more step, looking at all the net forces at C on ABC to figure out the correct answer. So we can put F1 on this rigid object or this rigid object. We can put it on either one, but we got to do that one last step to figure out what the net force on ABC is. Oh, and I see a question here in the chat. It seems like doing the whole frame is always the safe bet. When would you not want to do that? Maybe it's possible in this problem, but yeah, the FBD of the whole thing is actually a really good place to start. And there really is no answer of like, oh, when this scenario arises, you don't do the FBD of the whole thing. It's all about being able to identify all your FBDs and then just going through those. There's no really particular order to go through those in, but a lot of times, and I think the reason is because the supports are typically in a vertical line or they're in a horizontal line. And so because they're in that vertical line, we can solve for more unknowns. We can have 4 unknowns and still solve for things because 3 of those unknowns will cancel out when we do moment. So yeah, the whole thing, definitely a good option to look at, but not all the time. Like in this homework problem, actually the whole thing is not going to work because, you know, and part of the reason we know that is because it's, they don't really tell us any geometry over here at this thing, but we still want to think about this in terms of what are our rigid objects, and those are all of our options for FBDs. We talked about this last time, but note that the angle at F is 90 degrees. You have to know that angle right there of 90 degrees in order to solve this problem. So I have another question in the chat. Is it consider making an FBD of the whole thing if you were to split it in half? Yeah, if we're splitting it in half, it's not the whole thing anymore, right? And we are not cutting through any of our rigid objects right now. We are picking the whole rigid object. So like on our quiz question back here, you know, this is a whole rigid object. This is a whole, like, right? That's the whole thing. We're not cutting it anywhere or doing anything like that. We are only picking FBDs. We're not cutting through any rigid objects, right? We can separate them out, but we're not going to cut through or separate anything yet. We will learn how to do that, but that's really a different topic. Great questions. Okay, so that one, 90-degree angle. And then you see some homework problems here coming up. These are the ones due on Thursday. Look at all those different rigid objects. We need to be able to identify those if they're multi-force or 2-force, and then just go through them and pick, okay, how this FBD is going to have how many unknowns? How many knowns is it going to have? Does it have what I'm looking for? We just identify all the different rigid objects and then ask ourselves, okay, what if we drew an FBD of that? What would we have in that FBD? Would we be able to solve for anything? That's our process for all these problems. This next one too. Let's, you know, look at what about an FBD of this rigid object? What about an FBD of the whole thing? What about an FBD of this other rigid object? That is the best way to approach this. We've called it a complete enumeration, but it really works for everything. That's the way that I solve these problems. It's the way that I can look at any frame and I can say, okay, I know I have my process. As long as I can identify the rigid objects and I know what reactions go at each connection, then I can solve that problem no matter what it looks like. Okay, so our problem that we're going to do is this one. So we're going to look at this set of pliers. We looked at a simple set of pliers last time, and we talked about machines or systems designed to change the magnitude and or direction of a force. And we figured out that we had about a 7-to-1 increase from the force that I apply on the handles to the force that we get at the jaws from this simple set of pliers. Well, let's take a look at these pliers now. And so let's draw out all of our given information. One thing I've found that makes our drawings a lot nicer and a lot easier to do is to label the points first, where we know all the geometry, like point A, point D, point B, point C. And we look at this problem and it's just like, oh my gosh, there's so much going on. Like, where do we start this thing? Well, we're going to take it step by step. But for drawing the given information here, let me just I'm going to put point D right there. Let me put point A right there. Point C looks like maybe it's about right there. And then halfway between A and C, and then a little bit down from there is going to be point B. So there, I'm just getting my points on there. That's where all my geometry is relative to. I think I also have a point E, and that looks like it's probably, oh, I don't know, maybe about right there or so. So there's all my points, just getting my dots on the page there. Then we can start to combine, and not combine, but we can start to draw our rigid objects around those. Like this bottom jaw, let's draw this bottom jaw to the top handle. So this bottom jaw goes like this. It does go around these 2 points here. And then it wraps back and we have this top handle here. And so really, then it becomes less of a focus of, oh my, do our rigid objects look good? It's more about, well, do our rigid objects include the correct points that they need to include? So that's one rigid object. There's another rigid object here that goes around point A, and then it's part of the bottom handle. It includes point B right there. And so we can just kind of continue it off like that. So there's the bottom handle. And then we have another rigid object that includes point D and C, and that's this top jaw. So I just need to make sure it goes around those 2 points right there. And so there's my top jaw right there. And then I have one more rigid object. I have this rigid object that goes from there to there. So maybe it's not the prettiest picture, right? But it has everything that we need on there, and they're all relative to each other. And then we can we have our piece of wood right in here that we're trying to squeeze with these shears. Oh, and actually, let me move it over a little bit where I put that dot for E. So it's really right here, right? So right there is where we were saying it was. And then we can add some of our horizontal geometry here. We have these 3 distances. Like we know that distance right there is 1 inch. They tell us that this distance right here is 0.75 inches. And this distance right here is also 0.75 inches. We have our forces that are applied over here, and they tell us that P is equal to 2.42 pounds. We have another P up here that's also 2.42 pounds. And we have some vertical geometry that we can do. Like they tell us that the distance from there to there is 0.5 inches. And from here down to there is also 0.5 inches. Okay, so, and we want to find, for this problem, the normal force at E. For our solution, let's identify all of our rigid objects and their type. And this will be basically how we can pick our FBD. So how do we pick the FBD? Well, let's make a list here. And so we're going to have our rigid object, and we're going to have the type that it is. And the type, all we're doing is it a 2-force or is it a multi-force rigid object? So let me go to the front row here, E through H today. Brittany Ellington, give me one rigid object. Okay. Spencer Ayers, one rigid object. What's a rigid object that we have on there?
The top handle of the shears.
Yeah, the top handle. So, oh, you know what? And that reminds me, yeah, you don't have any way to specify that, do you? So let's label our points here. So this was point E right here. We have point A is right there. Point D is here. This is point C right there. And then this is point B. So yeah, that'll help us label. Yeah, so I think you're referring to E, A, D, and then I'm just going to call it all the way up to P. P doesn't have a point label, but we'll just say EAD to P. What kind of rigid object is that, Spencer, while I've got you on here?
Would that be a multi-force?
Absolutely, right? There's definitely more than two locations where forces occur. That's all we're trying to do here. Now, let me go ahead and what about AB to P? That's also a multi-force because it's got 1, 2, 3 locations. We have the top jaw, which is we'll refer to as ED to C. So we'll call E the top and the bottom. Really, E, I guess, is technically that that branch that we're trying to cut through. That also has more than 2 locations, so it's a multi. And then we have B to C. B to C is a 2-force member because there are only 2 locations of forces. So this is doing a couple of things for us. It is providing a list of options for FBDs, and it's also helping us so that when we draw the FBDs, we know, okay, if it's a 2-force member, well, that's a known line of action. So I shouldn't, like at B, I shouldn't do a BX and a BY. I should do an F from B to C. And so we get 2 things from identifying all those rigid objects. Okay, so let's use, so this is our complete enumeration, right? These are all of our possible options. Let's do some intelligent enumeration though, and let's get rid of some of these. Which are the only 2 that have known forces? Well, my only 2 that have knowns are these 2 right here. So actually we just went from 4 down to only 2 possible FBDs because, you know, ADC doesn't have any known values in there. B to C doesn't have any known values in there. We talked last time about, you know, we could look at the FBD the whole thing. The problem with pliers is when we have 2 equal and opposite forces, if we do the FBD the whole thing, those 2 equal and opposite forces end up canceling out in our FBD. So we aren't able to really solve for much when we do that. So we're not going to look at the FBD the whole thing for this one, but we certainly could think about doing that for sure. Okay, so now what if we did EAD to P? Let's look at that one. It has a known value. How many unknowns are we going to have at point E? Just at point E. At point E is just 1. It's a normal force. How about at A? At point A, we're going to have an AX and an AY because it's a multi connecting to a multi. So now we're at 3 unknowns. At D, that's also a multi to a multi. So now we're at 4, 5 unknowns. So we have 5 unknowns in this FBD right here. And so we'd say, okay, well, that kind of seems like a lot. Let's check A, B to P. A has 2 unknowns. B just has 1 unknown. And we have a known. So this one only has 3 unknowns. So we're going to start here. So we're going to start with that FBD. But that's how we should approach all of our problems. Identify all the possible rigid objects. That's our list of FBDs. And then just start going through them and saying, well, you know, first we can say which one has knowns, right? Because if it doesn't have a known, then we can just automatically eliminate it, at least to start with. Maybe we can use it later. But to start with, we need to have known values on there. And then I have a question in the chat. Why doesn't B have 2 unknowns? Because B to C is a 2-force member. And so I know my line of action of that force has to go from B to C. And I know the geometry of that line of action. So it's an unknown magnitude with a known line of action as compared to like A, where it's an AX and an AY because it's a multi to a multi connection. So I don't have a known line of action of that force there. Okay, so let's go ahead and let's do an FBD of A, B to P. And so let's see, what is this FBD going to look like? We kind of have the handle kind of curves like this. I'm not super worried about getting it, you know, absolutely accurate there. We have our 2.42 over here. 2.42 pounds is acting right there. Point B, we can say, is about right there. And there's our line of action right there. And we can draw this either direction. We can draw it going up and to the left. We can try it going down and to the right. We haven't drawn it anywhere else. So I'm just going to put it down and to the left, just arbitrarily picking that. We'll call it the force from C to B. And then here at A, we're going to have an AX and we're going to have an AY. Our geometry then includes, we have a vertical distance right here, and that is 0.5 inches. We have a horizontal distance from A to B there, that's 0.75 inches. And then we have another horizontal distance from here to here, and that is 4.75 inches. And I'm actually looking over at this picture over here, and I need to add, I'll highlight it. This was given to us as 4 inches right there. So I forgot that, but there I just highlighted it in our original given information, that 4 inches from C to P, right? And so we're going here, it's 4.75 because we're going from point B is right here to to P over here. And then FCB, if we look at the geometry there, it's a slope here of 0.75. We've got a 0.5 there, and then that makes the hypotenuse of this a 0.901. So we know the slope of FCB right there. Hey, take a look at that. We just went from this crazy set of pliers where we've got all this stuff going on to look at our first FBD. It's got 3 unknowns. It's got a known value on there. And now comes really the easy part. We can sum moments about A equal to 0, and we will find, we're going to be able to find FC to B. We'll make a positive going counterclockwise there. Our equation here, we would end up with a minus 0.75 over 0.901 FCB times 0.5 inches. So that's, I'm taking the X component of FCB and multiplying it times the 0.5 inches, that vertical distance there. And that's causing a negative rotation. We have, let's look at the Y component. It's a 0.5 over 0.901 FCB. And that is at a distance of 0.75 from point A. It's also going to cause a negative rotation about point A. And then we have a plus 2.42 pounds times that whole distance of 5.5 inches. And all that has to be equal to 0. We are going to find that FCB is equal to positive 16.0 pounds. So going back to that question earlier about why did we only have 1 unknown at B, why doesn't B have 2 unknowns? Well, because it's a 2-force member. Also, we needed to recognize that in order for this FBD not to have 4 unknowns. If we drew this FBD with 4 unknowns, that would be too many. Okay, so we found, now we have FCB. We could certainly find AX and AY as well. Let's sum forces in the X equal to 0. I'm not going to write out the equation. We're going to find that AX is equal to 13.3 pounds. If we sum forces in the Y equal to 0, we're going to find that AY is equal to 6.46 pounds. Okay, so now what do we do next? FBD of what? Because we still haven't found NE, which is what we are looking for. So let me scroll back over here. You can see the original stuff that's going on. We now know AX and AY, and we now know what's going on there. So we have 2 choices that touch E. We could do an FBD of this one up here because let's see, how many unknowns would that have? That would have a normal at E. It would have a dx and a dy. and we know FCV. So that's a known. So that wouldn't count. So we only have 3 unknowns. This, though, we have to watch out for is they don't specifically tell us the geometry. We cannot assume on this one, we cannot assume that this line right here, the line from C to D, is parallel to the line of those jaws. So they don't tell us. If they don't give us geometry, we have to stay away from it. We can't make up geometry here. So the other one that touches E is the bottom jaw to the top handle. Well, now that we know AX and AY, we're going to have 3 unknowns. It's going to be a DX and a DY, the normal force at E, and we have a known value of P over there. So our next FBD is going to be based on, again, the process of elimination, FBD of ED, what was it? EAD to P. So based on our process of elimination, we're going to do this FBD, which looks basically like this. It goes, we had our jaw, it comes up like this, and then our handle kind of wraps back like that. So in this one here, we're going to find we have a P of 2.42 pounds. At at D right here, we haven't drawn those anywhere else, so I can pick. I'm going to draw DX to the right, and I'll draw DY going up. At A, we have drawn those, and we did find their value, and so we know what direction we should draw them in. This A over here on our previous FBD, these are the forces that are acting at A from the other rigid object that it's connected to. So if AX is going to the right on this FBD, we have to draw AX going the opposite direction on this FBD because we found it to be positive, right? So we found it, yes, okay, we got a positive number here. We got a positive number here. So it is going this way on this FBD. So now AX is equal to 13.3 pounds. And then AY, we drew it up over here. So we're going to draw it down over here. AY is equal to a positive 6.46 pounds. So we're drawing them sign correct. If I had found like let's say AX I found to be negative, right? I originally drew it to the right. If I found AX to be negative, that means on my FBD of AB, it should be going the opposite direction. And so that means I would switch it still, right? So if I find a negative number, I got to take that into account when I'm drawing my next FBD. My AX would go if I found a negative number in the first FBD, my AX on this FBD we're currently working on would go the opposite direction. Okay, so we have AX and AY, and then we have the normal force over here at E, which is going down because this is the force from the twig acting on the jaw of those pliers, right? That's the force from the twig onto the jaw of that there. We see, again, we have 3 unknowns in this FBD. And if I sum moments about D, I'm not going to add the geometry and I'm not going to write out this equation. But if I sum moments about D, I'm going to find the normal force here is equal to 20.0 pounds. So the only step I'm skipping is actually writing out each expression for that equation. But that's all we have to do is take the moment about D. Everything else is, except for any is known, we can solve for the normal force at E, and we get exactly 20.0 pounds. Again, we started with 2.42 pounds, right? We applied 2.42 pounds to our handle. That's almost a 10-time magnification from that original applied P to the force that we're exerting on there. These are a pair of pliers that fit in the back of your pocket, right? These are only like 6 inches long, 5.5 inches long. So we took a machine that's only 5 inches long, and we get a magnification of almost 10 times. That's pretty cool how using multi-force and 2 force members and all pin connections, we can create this system that changes the magnitude and or the direction of the force. So pretty cool stuff. Any questions? use this same approach on your homework. Don't let the picture and everything going on intimidate you. If, just take it and say, okay, this is this, I can do this FBD, I can do this FBD. Really focus on drawing those FBDs. It's going to make the exams way easier. It's just going to make your life way easier as well, right? And if you're not getting the right FBD, then you really, that's the step to focus on, because the equilibrium equations, summing moments, we've done that probably hundreds of times by now at this point in the semester. Okay, let's move on now to our next problem, another machine problem here. Again, it looks totally different, right? And let's use the same approach though. So let's write down our given information, and then we'll jump in to solving this one here. For the handwritten homework, remember, you can take a screenshot, copy your image, for given information. If you don't want to draw all these, that's totally fine. However you want to get that, that given information under there. You don't have to hand draw them. I like to hand draw them in class. I think it's a nice skill to have. It also, emphasizes the different rigid objects within our system, which I think we're all seeing as super key. So let's put point A here. Again, I'm going to draw the points here. Let's put point D about right there. Point C is kind of in between A and D. I don't know, about right there. Point E is kind of weird. It's like in here. It's definitely to the right of point C and below D. So I'll put point E right there. And trying to emphasize that it's not that C, D, and E are not in a straight line. And then point G is probably about right there or so. And that'll at least get me started with drawing some of this stuff. So I can draw, there's the bucket of this backhoe right here. So there's our bucket, is like that piece that goes around those parts right there. And so what we're asked in this problem is we have this bucket of the backhoe, and it can have a weight of 1,200 pounds and a center of gravity at G. Determine the forces in the hydraulic cylinders A to B and in links A, C, and AD in order to hold the load in the position shown. The bucket is pinned at E. So they're kind of giving us a little bit of information there about E. Okay, so we have, they also tell us that this is a short link here. So that's a rigid object right there. They tell us that this is a short link right there. So that's all one rigid object. And then they have this, this hydraulic cylinder that kind of goes up at a 45-degree angle. So let's just try to draw it at a 45 right there. This hydraulic cylinder, you can draw a line there if we want to make it look a little pretty. And then it goes into this point B right here. And we do have some other rigid objects going on up here. This one kind of connects down. It wraps around here and comes back. It goes over D and E, doesn't it? So let's make sure this one goes over D and E right there. So look, something like that. But notice that they stop labeling the pins up here, and they stop giving us geometry for this stuff going on up here. And remember, if we don't know the geometry, we can't use it there. So there's our general system. Let's get some geometry on here. Well, they tell us that this angle right here is 45 degrees. They tell us that this, basically what they're telling us, this angle right there is equal to, it's 120, but we got to subtract 90. So that's 30 degrees right there. And then they give us a couple of horizontal distances. So they tell us like this distance right there is 0.25 feet. And then all the way out to there is 1.5 feet. And then they also give us this vertical distance from C to E. So from there to there, they tell us that that is 1 foot right there. And let's label our points. So this is point G is out there. That point right there is C. This point is E. That is point D. And this is point A. And this is point B. let's see, we could D, E, F. We could call this, if we really wanted to, we could call that point F. We have a G, and then we could call that point H. But notice I'm not even drawing that other stuff because, like I said before, they don't give us any geometry. We don't know those distances. And actually they label point B, but they don't even label those other points up there. So this problem looks totally different, doesn't it? Let's add our force here. They tell us that this is 1,200 pounds. And they want us to find, for this problem, they want us to find AB, AC, and AD. What is similar about all three of those members that they're asking us to find here? Let me see somebody from the front row here. Is Garcia here? Adrian Garcia is here. Okay, I was thinking of the other one, but Adrian, yes. What is common about those three?
Can you repeat it again? Sorry.
Yeah, what's common? They're asking us to find the forces in hydraulic cylinders AB and in links AC and AD. What is one thing that we can say about all three of those things? Has to do with the type of rigid object.
They're all two force members?
Yeah, they all are two force members, right? Short link, anytime we see short link, that's a two force member. Anytime we see a hydraulic cylinder, that's a two force member. We can also look at it too, and we can say, oh, each of those only has two locations with forces. And so, yeah, those are all two force members. So they're asking us to find, everything they're asking us to find is forces in two force members. Okay, so for our solution though, again, let's set up all of our rigid objects and their type. Well, Adrian got us going on those three, the AB, the AC, and the AD, and those are all two force members. For all three of them. What's another rigid object that we have on there? Well, how about the bucket? CEG. That's a multi-force rigid object. And in fact, it's the only one with a known force, isn't it? That 1,200 pounds is like, hey, pick me. I'm your FBD because we have a known. This is the only one that has a known force, is that one right there. And actually, we are never going to draw an FBD of a two force member. We would never just take AB and draw an FBD of it. Because the only thing it's going to have is it's just going to show like compressions going on each side or tensions going on each side. We always need to look at those multi-force members for our FBDs because those are the ones that have the known values on them. So that has a known. How many unknowns is it going to have at C? How many unknowns is it going to have at C? Is it going to have one or two? Let me ask somebody else from the, oh, Simone already said, yeah, it's just going to have one because A to C is a two force member. How about at E? How many are we going to have there? Are we going to have one or two right there? Anyone? Go ahead, throw it in the chat. Simone, even if you want to do it again. Luke, yes, it would have two because what kind of rigid object is this one up here? They don't tell us much about it, but they do give us enough information to say that that is a multi. And so it's at point E, that's really a multi connecting to a multi. So E is going to have two unknowns. It's going to have an EX and an EY. Okay, let's do our FBD here of CEG then, because that's a total of 3 unknowns in that FBD. And so let's see, we have point E is about there. I'll put point C there, and point G will be about right there. So we have this part, and then we have the bucket here, right there. And so there's our bucket. We can have our 1,200 pounds is going to go right there. We talked E is going to be an X and a Y because it's a multi to a multi. And so EX and EY. And then over here, A to C, well, that's a known line of action. And we can draw it in either direction. I drew it in my, just to be consistent, I drew it down and to the right. And so that's our FAC. It's that 2 force member. And actually, that's one of the things we're trying to find, right? We're trying to find the force in A to C there. Let's add our geometry here. We have a distance there to there. This distance right here is 0.25 feet. And this one right here was 1.5 feet. And then they gave us the vertical distance was equal to 1 foot. Well, we're back into it again, aren't we? We're at our equilibrium equations. That's really the easy part. It's picking our FBDs that are the difficult part, or the part that we have, maybe not difficult, because I think if we use this complete enumeration, then it doesn't need to be difficult, but it can be the part that we need to spend more time thinking about, that we need to break down and spend our time with that. And then once we get to the equations, it's just a matter of really just plugging and chugging into those equations. Oh, let's see, I've got some more geometry here. We identified this angle right there was equal to 30 degrees. Okay, so, but we can see now, and I'm gonna just skip over the equilibrium equations. I'm gonna start with summing moments because I can get rid of lots of unknowns if I sum moments about E. And I'm gonna find, when I do this, the FAC is equal to a positive 2,512.19 pounds. So I just found FAC. Now we could certainly, some forces in the X and some forces in the Y, we could certainly find EX and EY, but do they ask us for EX and EY? They don't. And not only, and I don't think it's gonna help us either with our next one. Now we need to pick our next FBD. And this is kind of a unique case here where we now have A to C, and we need to find AB and AD. So we still need to find, how are we going to find AB and AD? What FBD? What FBD of what? Any ideas? Anybody see where we could go from here? Point A. Now this is a little bit different than what we've been talking about. Luke is specifically saying a point instead of one of the rigid objects. And actually this is like, these are all 2 force members coming together. That's like a truss connection. That's a joint. So yeah, let's do the FBD of point A there, which is a little bit different. This is one of the few machines where you see doing an FBD of a point right there. But that is going to have 1 known and 2 unknowns. They all intersect at A. We have 2 equations of equilibrium to be able to solve for that. Now FAC, let's figure out, we figured out FAC. How did we draw it over here on this FBD? Right here, we drew it down. What kind of force is that? Is that a pushing force or is that a pulling force, the way that we drew it? It's drawn as a pushing force, right? Isn't it pushing on our rigid object for FBD? So it needs to switch direct. It also needs to be a pushing force up here. And so our AC is going to be in compression because it's a pushing force. So it's going in the opposite direction, 2,512.19 pounds. Now AB and AC, we haven't drawn those anywhere else. I'm just going to go ahead and do those both in tension. It doesn't really matter, but that was our process that we did in trusses. We have our FAB, FAD. We've got all our geometry here. Like we know this is a 45-degree angle. We know this was a 30-degree angle, even though it doesn't look like it on my picture. But there's our next FBD there. And we can now sum forces. If I sum forces and the y is equal to 0, we're going to find that FAB is equal to minus 3,076.8 pounds. So that's just telling us that it goes opposite as drawn. And then we can sum forces in the x now. And the reason I picked forces in the y first is because I only had one unknown in the y. I have originally I had two unknowns in the x. Well, now that I found my FAB, I only have one unknown in the x. And when I plug that in, I'm going to find that FAD is equal to a positive 3431.7 pounds. Now, remember, I found the FAB of negative 3,076. So how do I handle that? I didn't explicitly write out my sum of forces in the x. I look at, when I come up with the equation, I look at my FBD to figure out if FAB is negative or positive. It's going to the right, so I would call it positive, but then I would plug in a negative 3,076 into that. And then just to reiterate also, the FAC over here, this shows up in this FBD as a pushing force. So that's a pushing force. We found a positive number for it. So it means it's going in that direction. So then I drew it over here also as a pushing force as well. We've got to watch those when we're going from one FBD to the next FBD, that they're going to go in opposite directions. And we also need to be able to handle it when we get a negative. If I had gotten a negative for FAC, then I need to know, oh, okay, well, it actually goes opposite as I drew it here, which means it's a pulling force. And then I would have drawn it over here as a pulling force, also going in the opposite direction, right? So if I found a negative, I would have flipped it in that FBD of A. Okay, so we've gone through some really good examples here. The illustrating, we can follow this same approach on all of them. It's all about identifying the rigid objects and picking those FBDs on there.